Hey there, I'm Alejandro, and welcome back for day 193 of me doing Daily LeetCode Challenge. That's every 20 years worth of Greek contributions here on GitHub. So today's poem is January 25th, 2025. Without further ado, let's get straight into it. Okay, today we get LeetCode medium problem 2948. Make lexicographically smallest array by swapping elements. You're given a zero-indexed array of positive integers nums and a positive integer limit. In one operation, you can choose any two indices I and j and swap nums I and j if nums of I minus nums of j is less than or equal to limit. Return the lexicographically smallest array that can be obtained by performing the operation any number of times. Wait, if I can do that, can't you, wouldn't it be enough if limit is greater or equal to 1, can't it? Yeah, so here, oh, limit is 3, but you can't sort the full array? That's weird. Can you not continuously make it? A return that can be obtained by performing the operation any number of times. Array A is lexicographically smaller than array B if the first position where A and B differ, array A has an element that is less than or corresponding to the element in B. For example, the array 2, 10, 3 is lexicographically smaller than the array 2, 10, 3 because they differ at index 0. Wait, so why is it the case that if it's not that limit is greater or equal to 1 that you can always just return the sorted array? Apply the operation 2 times. Swap nums 1 and nums 2. 1 and 2, sure. 0, 1, 2, 3, 4. 9 and 8. 8 and 9. Okay, why can't I just, swap, I can swap 1 and 2, 1 with 18, 1 with 6, and 1 with 7, right? Can I not do that? Zero with 4. Oh, not if the index difference is less than or equal to the limit, if their value difference is less than or equal to the limit. I see. If their value difference. Okay. I see. So nums of 1 and nums of 2. 5 minus 3 is 2, so you can indeed swap those. That's kind of crazy. Okay. Because, yeah, if it was index difference, then obviously you can just bubble sort your way as long as limit is greater or equal to 1. And, yeah, limit here in case is greater or equal to 1. So if it was index differences, then you're chilling. It's about number differences. So, yeah, here you can't really get the 18 past, and you can't really connect the ones, right? Are you not gonna do some bubble sort-ish like of idea? Where here's 1 and 5 is already in sorted order, so you don't do anything. 5 and 3, you ask yourself, can you switch them? And you can, so you do. Then 5 and 9, can you switch them? You can't. 8 and 9, you can, so you 9 and 8, you can, so you do. Is it as easy as that? You have a current index, but a current num that is actually there. N is equal to length of nums. I in range n will do n minus 1. Would it be something like greedy? Yeah, 1 and 7 you can't. 7 and 6 you can and you should because it would make it more sorted. 7 and 18 you can't. 18 and 2 you can't, 2 and 1 you can't, and it would indeed give you this array. Here, if we did that, 1 and 7 you can't. But it's already sorted, so you don't care. 7, 28. Okay, yeah, and the length of the numbers is linear, right? So you can't even do n squared in the first place anyways, right? So it really kind of limits your options. Like you're not going to start going into a DP kind of mindset. And so you must do something linear or n log n. It could be like some divide and conquer kind of approach here. Yeah, because actually, whoa, wait, no, this is bigger than this is. I can move a number to wherever I want in the array. Oh gosh. I can move it to wherever I want in the array. I don't have to do things side by side. Although, I mean, it's worked in these examples. Would it have worked here? Can't swap. Can't swap. Can't swap. You just can't swap anything. I mean, it works for these examples. Okay, we might have as well tried. Like, this is a greedy idea. Although, yeah, this is scary because this means you can move anywhere in the array. So maybe it might not be wise to just do things that are local. But, like, you know, something like bubble sorted in the first place is an algorithm that, like, is able to help you sort. Is that obviously in that case, it's like you are able to swap anything you want. So you can bring the max to the right side and so on, da. Here we're just doing a linear scan and asking myself, like, can I swap, right? Advantageously. Maybe when I swap, I should, like, try to go backwards as much as I can. But then in the worst case, it brings me into, like, n squared territory, right? So maybe not the real idea. Okay, let's try the greedy idea because it does work on these three examples, and if we're lucky, it does work in the general case. So again, it's pretty much greedy, right? But the annoying thing with greedy algorithms is proving that they're correct. But here on LeetCode, you know, we can kind of get away with greedy proofs by just, you know, running the test and seeing if we get lucky. But it's not good to do in practice. But hey, you know, well, I'll take any advantage I can get by doing these daily LeetCode challenge problems. So yeah, here I'll just do small num, big num, nums of I plus 1. If small num less than or equal to big num, then we're chilling. Otherwise, if so here assert small num greater than big num. So if small num minus big num less than limit, less than or equal to limit, then nums of I plus 1 equals, did I mess up there? Small num. Big num, comma small num. Return nums, right? So that's kind of my idea. So this seems to work in the three examples that were given. Yeah, that's accepted for those, but is it accepted in the general case is really the question, right? Yeah, so it's not accepted in the general case. Okay, makes sense. Makes sense, because the point is it can jump anywhere that you want in the array. Yeah, that's kind of annoying. Here we can say changed equals true. While changed, right? We can do something like this. Changed equals false. Changed equals true. Right? So something like this maybe. How about that? Still wrong, really. Okay, so there's something a bit more clever to do here. Okay. Let's think, eh? 160, 34, 84, 62. So I want 56 to come here. But not 34. And what was the limit? The limit was 4. So should I like store for every number like the number I ideally like to have? Maybe, do I do something like this? where I sort the elements themselves. And then at every number, it's like, okay. Okay. For every single number, I say, like, I'm at every single index, I'm like, okay, at 1. I want the very first number that is, yeah, and also it's lexicographically smallest, right? So if you can put the smallest possible thing in the very beginning, that's awesome. That's absolutely awesome, right? So you should definitely be greedy in that aspect. So, okay, I have an idea, which is the very first thing we're going to do is sort the entire array. So idea, sort all of nums. Then for each each index num valid replacement you can find. Number that is greater or equal to num minus limit. This can be done with leftmost binary search for every single number, which is n times log n total operations, which is the same as the sorting. Okay, so that's kind of my idea. So here we'll say sorted nums equals sorted nums, and is equal to the length of nums. That should probably go first. Then we'll say we should map numbers to their indices. Are all the numbers unique? You can't really assume that, right? We can't really assume that the numbers are unique, especially because it doesn't say so on equals trace. Okay, that's fine. Right, because when I swap two numbers, like, I want to make sure that I never use that index again. But like when I swap the index is no longer the same as it used to be, right? That's about their new indices. Because I want the first smallest, but that hasn't been used. Do I do num and index pairs? And that's what I sort. This is interesting. I feel like I'm on the right track. Right, where I want the best thing at every single time. Now I'm just gonna make sure that I know how to band things. When I swap two integers are not necessarily unique, which is a bit of a problem. You can keep track of their indices. The only thing is that indices can change. It's a problem for each number. We'll do a set, right? Say for num and nums, we'll say we can apply leftmost binary search. Okay, L comma R is equal to 0. Actually, num itself will be greater or equal to num or limit, so we don't have to worry about a non-existing solution. Num is the number itself. Num is itself. That's one solution. There you go, so we don't have to worry about that. Well, L less than or equal to R. Nums of R very equal to num minus limit, basically. Anyways, we'll say to L plus R over 2 if nums of mid greater or equal to num minus limits. Valid solution. Keep searching for even smaller ones. Leftmost equals mid. It's mid minus 1 else. Valid solution. Larger values. L equals mid plus 1. Then we'll say most points to the only problem is if the number's been banned, or if the index has been banned, which also screws our binary search here. That's a bit of a problem. Okay, that's a bit of a problem. That's a bit of a problem. Most points the best available number. Yeah, that's a bit of a problem. Wait. Well, it is not, in band and leftmost. This is just not going to work. Yeah, this is just too much. Yeah, that's just not gonna work. Yeah. Oh boy, how is this not true? Oh, sorted nums of R. Sorted nums of mid. Sorted nums of leftmost. Oh, and I'm not even swapping that index. Yeah, this is just terrible. Okay, I need to think about this a bit better. Yeah, I'm not even. Yeah. This is just terrible. Okay. How big is limit? Okay, limit is huge. Oh gosh. Okay. Okay. We definitely need a loop through each number and know exactly what to swap with, right? We obviously can't iterate through limit. We want to do it with the smallest number. But that also preserves the criteria. Also, what if it's like, you need to do a series of hoops? Right here it's direct, but what if you need to do like jump, right? Right, what if you have like, oh boy, limit equals 2, right? And then you have 3. No, because if this is smaller than 2 of that, then there is going to be some element of convenience. Where it's like if it doesn't work for one, you won't be able to cheat your way through and so on. So yeah, we do also have to keep in mind that there's going to be a linear or n-log n solution to this problem. So yeah, we're probably not going to get screwed in cases like that. So we might as well not think about them too much. Just that this is an interesting problem here. Probably was on the right track with binary search here. I'm not even going to lie. Some idea there. Now, if I find the smallest number that's greater or equal to num minus limit, it actually doesn't matter what I do. There should probably be nums by comma I for I in range n. Index equals 0, 1. Yeah, we're just gonna do best index. Oh boy. Yeah. If not, I greater equal to best index, f string I equals best index equals nums of I equals nums of best index equals. Zero, 1, 2, 3, 4. Here I can probably just do something like continue. Interesting. I'm actually really close. Or yeah, or if best index. I'm actually very close. I have everything except those two. What's going on in these cases? Do I ever have 1662? Don't. This is a very interesting problem, right? Yeah, it's just... Oh wait, let's think about this. I is larger than best index, right? I gotta assume that I've already found my best solution for the best index. Right, like I don't want to go backwards. I'd rather help my left stuff. Although it did even seem to do one bit of a change. Yeah, this isn't changing anything. Where's 1662? I want to print this every single time. Alert, print, alert, stop. The indices swap. The indices swap. Oh, that's so annoying to take care of. I can't do things this way instead of sorted nums. Oh, mate. Oh, mate. And the numbers aren't unique either. It's just, okay. Okay. Oh, wow. Wow, that is a lot of hints in case we need them for this problem. Okay. Okie dokie. So some tactics that we need up in here. Some tactics for sure. So yeah, this is a bit of a problem. It's just so annoying. I can't map numbers to indices or indices. Maybe I do I. Well, that really worked out real good for me, eh? Oh, it's because of this. It's like, yeah, I have to keep track of transformations. Oh my gosh. So okay, I do have a working algorithm. Obviously, in here, I can't have an O of n operation. Yeah, okay. So I actually do have a working algorithm. It's just the indices are getting messed up because of the fact that I swap them. That's pretty darn annoying. Obviously, yeah, this is going to TLE me, right? Yeah, this is going to TLE me for sure. Ugh. Or wrong answer me. Jeez. Jeez. Wow. 375. Here I'll do nums. Yeah. I'm close to some correct idea here. I will just need to find out what to do. I wonder if can I use some sort of hash map here? Or is something like this stopping me here? does nothing, right? Does nothing. String sorted nums equals. That's always a good thing to print. Maybe I can also do that, right? No, that is the idea. The best thing you can fit. Right? Right. The smallest number that's greater to the num minus limits. Num being one of them as a convenient side effect. Should work. Always an ambulance. This is quite tricky. Yeah, there's gonna be some idea here, right? The idea that I'm thinking of here, right, is that, like, you know, for something like this, it's like, okay, well, you have a limit of 2. So if I could put a -1 in there, that would be spicy good, right? So I find, you know, the smallest number that is greater or equal to -1. At worst case, it'll be 1 itself, which is guaranteed to be, like, you know, within that limit threshold, right? I know, worst case, we don't move anything. So it's like, you know, the number that is greater or equal to that threshold, like, you know, the first one will always be valid because at worst case it is the number itself which is valid. So there's a convenient side effect to that. Yeah, the only thing you must remember is bannings. By the time I get to 15, goes none, just in case. Yeah, okay, just not using this target. Ooh. Not best index. Best index is not continue. Interesting. Very, very interesting. Extremely interesting. I really should. No. I shouldn't do my binary search. I shouldn't do my binary search. I have to remember sorted. It's just that a sorted number might be bad. Might have been swapped already. It's so frustrating. Yeah. Maybe I do something inefficient. I just like use a heap. It's like I keep popping until I have something valid. Make the swap with that valid, and add everything else to a heap. Just it's inefficient, but I might as well do things right. Just a heap of available stuff. Heapify min heap. The nums. Nums of I. Too small. It's just terribly inefficient. Like I'd rather just have the sorted array from the start. Or maybe I use maybe this is when using an AVL tree is good. But do I really write my own tree, my own self-balancing tree just for this? I probably should learn to just write my own AVL tree at some point, right? Like the point is that for the very first index, I swap it with literally whatever is best and go on. So maybe I do something like this. Is number and index pairs. And then once I've used up a number index pair, I've used it up. This is just okay. This is tough. Or close. But it's tough. It's tough. Sort of nums. How do I do this? It's like I can't I can't keep track of the indices in the band set because I'm literally moving the indices. It's just so ridiculous. Yep. Maybe this will be a better indicator. And 1570. No swaps happen. No swaps happen. Wait, it's literally the sorted thing except 275.87. Yeah, here there was some swappings. Okay. Five and two. Eleven and two. Okay, that does not make sense. Yeah. I need to keep track of like the indices and the indices swaps and everything. It's like I need mappings, right? I need mappings. I need big time mappings here. It's just I'm getting annoyed by the fact that things are not clean. Yeah. When I swap two numbers, it's a big deal because I can never swap that number again. Right, we could also just do it by, by uniqueness. Is equals set. Here we can just straight out ban numbers. Well, that could have been a problem before. To add best index every single time. That should not be banned. Doesn't matter though. Doesn't matter. I'm stuck in a feeling. Stuck in a feeling. Hallelujah. Okay. So yeah, if this is the case, continue. You cannot swap with something that's before you. You must swap with things that are greater than you. And here we'll do that. Like if something like this works for these cases, wow, it does not even work for these cases. That is actually kind of wild. Continue. Well, did not work, eh? Oh, oh, nums of mid not in band. That'll be kind of brutal, eh? Can't get this to work. Yay, yay, yay. Yay, yay, yay. Okay. Idea is very, very, very simple. For each number, put the best one you can in there. That has not been banned. That has legitimately not been banned. But for the life of me, I can't figure out how to do that. Cannot figure out how to do that. Ay, 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 ay. It's because when I swap numbers, things are banned. It's the same problem, I'm realizing. Okay, I'm just going to restart the problem. I don't care. I don't care. It's okay to think about this. Right from 1. I want the first number to square equal -1. Now once I find that first number, I can never use it again. Here n is equal to length of numbers. Ein range. Find best replacement. Now, when we find a replacement, well, for now we can just make this quadratic, right? And just test that our hypothesis works, right? For j in range, I plus 1, comma n. I and j works, and j is a better number. Yeah. You'll say, alright, nums of best index, so best index, nums of I. Right, okay, so something like this does work, right? But it's too slow. Wrong answer, really? It's not even that it's too slow, it's wrong. Multiple. Wow, yeah. Multiple switches can happen, yeah. I'm thinking of this problem in the complete opposite direction, mates. Wow. Okay. Yeah. This is harder than I thought. Yeah, this is rather crazy. Okay, this is a much harder. I'm realizing this is a harder problem. So you can do multiple hops, right? So, okay, I don't even know how to even go about doing something like this in DP. So let's not even think about that. Okay, maybe we map things as dependencies, right? It's like, with a number, we let ourselves know what are the numbers I can. The only thing is that limit is huge, right? I can't do n squared preset work. Although I'd rather brute force a correct solution in n squared time and then figure out how to do it in O of n and n log n time, right? Right? Is it one of those cases where? Okay, let's think about it. Yesterday we got like a graph-like problem. What if we were in a graph-like type of thing, right? Because now I'm thinking like, okay, if these are dependencies, and I want to make it point to like, from biggest to smallest, where it's like, in terms of possible things, or like, from smallest to biggest, in terms of like, things that are actually possible, in terms of n degrees. If you can't swap, you can't swap. It's just, I don't know. This is a stretch. I don't know if this is a graph problem. Oh, it doesn't hurt trying to think about it that way, because it's not like I have many better ideas. Right here, it's like I can do something like this. Changed was true, while changed doesn't equal I. Changed equals true. Changed equals false. Does this work? Yeah, so that works. But now this is definitely too slow, right? But here, like, at least I might get like a TLE instead of a wrong answer. Because now I'll do as many rounds as I need to, bro. Yeah, okay. Now at least we're at a face with TLE instead of the wrong answer. Yeah, this is just crazy. Oh boy. Oh boy. Okay. Yeah, what if I map things in terms of dependencies, right? Maybe I can think of it as a bidirectional edge. Like, you can swap these numbers. I make nodes. Just do I really have to do n squared work to set up edges? It's just this crazy. Unless I sort the numbers and then it's like I know for a fact. But then I can go up the limit and limit is huge. Oh my gosh. Just like, come on. I guess for each number I could do like log n to find like the max index that is in range, and okay, technically if I really wanted to I could do log n work for each number and then send log n, right? After sorting the whole numbers. Jeez, mate. And what good would this do me? 5 things pointing to one another. Like it would be nice in that like from 38. But what needed to happen? I need to go from 52 to 38 so that 38 can then go to 27, right? So the point is that I want to think of it as a chain of dependencies where like 52 points to 38 and 38 points to 27. It's like, how deep can I go? What leaf node gives me the best value? Right? Or I do things in reverse and then it's just like I do like a topological ordering. I was just like, mate, what about like, you know, what about like, you know, not swapping indices and this and that and blah, blah, blah. Something like what I should ask myself, right, is like basically. I have to do this like this. Right, where here it's like I could do something like this. Changed equals true. Well changed. Changed equals false. What? I can make it more local. Yeah, so I can make it more local is one thing. So it's like I can focus on one thing at a time. Right, but here I can't do something like suffix mins or whatever so because I'm always updating stuff, mate. It's frustrating as hell. But yeah, the idea is like from a certain index, like keep hoppity hopscotching as much as you can, right? The only thing is that like I can't keep track of like, you know, a sorted list because I'm just gonna keep shuffling indices like crazy. If I keep track of a min heap, I'm gonna pop and push way too much. Like the idea must be I must be on the crux here, right? Like the idea is from an index, like, you know, keep swippity swooping, swapping until you can't do any better. No, maybe it's something like a min heap is perfect here, right? Should be a sorted array based on what you have left. Like a tree is actually perfect here, mate. Maybe I just genuinely build a tree. Like a self-balanced tree. Like an AVL tree, where it's like I can do whatever the heck I want. I can push and pop, query. Un, deux, trois petits chats, trois petits vilains grippons, entrés cette nuit sans un bruit dans ma maison. Il était un petit... I will need. Yeah, the only thing is with something like that was my research mate. I swap two indices. But I can't be swapping things in a sorted array because array ain't sorted anymore. And if I start adding some bands and stuff, I don't keep the sorted array property either. It's just so frustrating. It's like exactly not enough. Un, deux, trois petits chats, trois petits vilains grippons, cette nuit, sans un bruit, ont rentré dans ma maison. Keep swoopity swooping. Yeah. Let's think. I might not be able to do the smallest number, right? Remember to find the first smallest number that I can. Then as I push back elements to the heap, I'm going to keep going down as much as I can. Yeah? It'll be a solution. I might as well do it. Even though it's going to be bad. For number nodes. Heapify, min heap, range, add, equal numbers. Just how much swapping is gonna go on in here. This is a dumb solution. Mate, come on, I gotta think here. Oh yeah. Wait. I'm confusing myself here. I should be doing things this way. Even if every number was unique, it doesn't help me. Maybe I do need like a graph and like an ability to swap nodes in the graph, maybe, because like, Jesus Christ, I swear, mate. But no, even if I cache the smallest node, as when I swap nodes, it messes everything up. It messes everything up. Literally everything. I must do this in linear/nlogn time. Mate. I want the smallest possible number I can get at the beginning. I need a way to hash things, otherwise things are impossible. Maybe I make each num an object. That way they are hashably unique. And when I switch them, maybe things could happen where I can get a solution. Abuse Python object notation. That might not be a bad idea. Wait, that's actually pretty great. We can abuse the fact that classes have a unique hash. 1, 2, 3, 3 little cats, 3 little villains, malicious, wanting candy, trick or treating in Halloween. 1, 2, 3, 3 petits chats, 3 petits vilains grippons. De nuit, on rentrait sans un bruit dans ma maison. Let's see this. Well, that's pretty fantastic, eh? That would indeed make me feel like a go-go Power Ranger right there. 1, 2, 3, 3 petits chats, 3 petits vilains grippons. Cette nuit, sans un bruit, on rentrait dans ma maison. But even if I have unique hashes, it does solve one of my earlier problems, but does it solve all my problems is the question. Because I have to think about the multiple swishes. Where it's like I have to do leftmost binary search, but I reset the binary search. Right? Where it's like, I gotta do for I in range. N is equal to length of nodes. Mid is equal to L. things can be bad, mate. I'm actually gonna go crazy. Um, the fact that things are bad will break my sorted property. It's clear. It's so clear. What I need to do is continue the chain. I have multiple ways to think about this. I can think about it as a graph with dependencies, find the lowest thing, but then when I swap, I am screwed. Swapping has been the problem all along. Swapping. It messes with state. That's very annoying. Extremely annoying. Unreal levels of annoying. Maybe I'd take a break as well. It could be nice for me to take a break. Yeah, it's clear to me that you're always going to really want to put whatever you can that is smallest in the very first index. But it's just like, you just messed up everything after every switch you did. I understand that, like, okay, maybe after you do a switch, somehow you unmess up state, but I can't just randomly delete some random index without it being, oh man, inside of my array here. That is sorted. It's just terrible. It's just terrible. Yeah, I'm stuck. Okay. I don't know if to read the hints or just, take a break. Because it also is getting late at night. Maybe I take a break, get some Greek yogurt in my system. I don't know. I'll say yeah, okay. I might take a break, and then once I come back from the break, it's like maybe I just look at the hints anyways and so on. But for now, I'll just take a break and eat some Greek yogurt. And if I come back from the break and decide to look at the hints, no problemo. That is what we'll do, right? If I decide like, oh no, let's try something new and so on, blah blah, that's what we'll do. But you know what? I'll leave it to future me to decide and so on. For now, I'll just take a break, a little bit. It probably won't be too long, right? Between like 5 and 15 minutes for me, but just take a little break and figure out what I'm gonna do, and I'll let you guys know what I do. So for me, it'll be a few minutes, but for you guys, I'll see you back in literally just 1 second. Okay, hey there, I'm back. I was debating whether or not I should just wait till the next day to continue this and so on, because it's already around midnight, and not gonna lie, tomorrow morning I really want to get to play some pickleball. I just got a brand new paddle, which is the Diamond 60 16 millimeter control double black diamond, whatever it's called, new paddle, because I had a broken paddle and so on. I got to try one night. I had a lot of fun, and since it's Friday and tomorrow morning is Saturday, I want to make sure that I get to play when there's not much activity and so on. So I want to make sure that I do this problem so that I don't have to worry about it tomorrow. And yeah, since it's late at night and we've already spent an hour and a half on it, I'm guessing I'm probably not going to get the right idea, so I think it's time to look at the hints, right? I was debating again, like, whether I should wait till tomorrow or look at the hints, and I don't really have like a legitimate excuse besides I just want to play pickleball tomorrow morning, which, yeah, you know, maybe not the greatest excuse in the world. But hey, it's okay for just this once. So you know what? We'll go straight away. We'll peek at hint number 1, and we'll peek at it as however many hints as we need, and we'll just try to get this problem done by tonight. That way, I do not have to worry about it, and I can just get it out of the way. So there we go. Let's start off with hint number 1. Okay, construct a virtual graph where all elements and nums are nodes, and the pairs satisfying the condition have an edge between them. That's super interesting, because I did start thinking about this problem as a graph problem, although I got turned away by that idea at some point. Or even my last idea was this, although I was doing nodes not because I was thinking of it as a graph problem. I was doing nodes because I wanted to essentially have things that had a unique hash, where it's like, since the numbers are not necessarily unique. This isn't because I was actually thinking of it as a graph problem. I was thinking of this as a hashing, although at some point in the video I did think of noting these as dependencies and so on. But even when I was thinking of doing this as a dependency thing, I was still worried where it's like, okay, if you go down the chain, like, obviously it's like, you know, if you point to a bunch of nodes, you want to get to the deepest node that you can get and switch with that, but then it still messes things around in the graph problem. I guess it's like you can find the deepest nodes and switch the values. Actually, wait, you could definitely just do that, right? But then it's like, from a node, you'd have to DFS. And changing the val probably, does it change the hash? Or is the hash based on like the memory address of the like, this is where I guess the point where we abuse Python. Okay, we might as well just look at hint number 2 and keep going. Okay, instead of constructing all edges, we only care about the connected components. True, although I don't know if I want to whip out some Cosaraj's algorithm in here. Although I guess I can make things like, you know, undirected. So it's like, in terms of directed components, I could just DFS between. Okay, if I just DFS between. Okay, this is interesting. This is not the direction I was thinking of going in this problem at all. I did at some point think of it as a graphs problem, but I wasn't thinking it in terms of connected components. Connected components. I guess it's like, in a connected component, it kind of gives you, basically, in a connected component, each of those values can hippity hop against themselves, right? Oh, is this going to be a disjoint sets problem? And it's just like, you remove a node from a disjoint set. But essentially, you have connected components, like maybe like a min heap per connected component, or it's like, but you need to know. Oh gosh, you need to know which connected component something is in. So maybe it's like a dictionary that maps to min heaps or something like that. So you can always pop the smallest one. So it's like, from a node. Okay. This is just weird, right? I mean, I could also just sort them all, because n log n plus O of n is the same thing as n times log n in terms of big O. Is it really that simple? There's no way, right? There's... But then, how do you know? How do you know? Do you keep track of a range? Then it's like, what if two elements fall into a range? Yeah, because here I'm thinking I need to construct the. Okay, let's look at the hit 3. What is a DCU? Is that disjoint set union? Is that what this is? Hint 4. Sort nums. Now we need to just consider if the consecutive elements have an edge to check. Oh my gosh. Okay, let me move myself. Sort nums. Now we just need to consider if the consecutive elements have an edge to check if they belong to the same connected component. Okay, yes. That's all connected components. A list position consecutive elements after sorting. For each index of nums from 0 to nums length -1, we can change it to the current minimum value we have in its connected component. Yeah, okay, this was obvious immediately from the fact. Okay, so it says the first thing to do is, okay, nums.sort. Fine, sure. Or, wait. No. How do you know if it's in the same connected component? Is it like a range each time? It's like if it overlaps. Okay. Now we just need to consider if the consecutive elements have an edge. I see. But that's like I gotta update that range each time. I equals 0, while I is less than the length of nums than n. Create new component. Over here. Lowest operator. Okay. Here, this can all get commented out. Interesting. Right. Maybe I have the indices point to a component. Right, this is great. This is great. I guess they're already in sorted order. Already in sorted order. Yeah, things are already in sorted order, so there's... Wait, so if things are already in sorted order, the smallest ones are already on the left for me. So here, if anything, I can make this collections.deck. What the heck? That was weird. That was weird. But yeah, now I have the, since again, a convenient thing of lists and things like collections.deck is that they're passed by reference. So I can make them, I can make each index point to the same thing. Great, great, great. Okay. Now what we'll say is res is equal to that. Here we'll say for I in range n, res dot append dot pop left will return pop left range n. Is in the numerator. List. That did not work. That's weird. Like those numbers are in the same connected components. Ah, yeah, no, this is y. Sorted nums equals sorted nums. Here I must do this. Here we'll do num comma index equals 0, 1. num. We're getting close. Really, 5 should be in the same connected component. So maybe we should have things as ranges. Ugh. What did these hints say? Yeah. This makes sense. What is this disjoint set union? Is that what DSU means? Yeah, I'm so tired. I just generally want to push through this problem. I gotta push through. Right. If I do things in terms of ranges. Although no, it's like I can keep track of putting things inside a connected component because I can sort everything. Okay, I'm gonna restart the problem. Here we're gonna have original nums. Well, I guess sorted nums. Okay, since we have S1 is less or equal to S2. Sorry, I'm just thinking very heavily here. 0. My eyes. My eyes. I got this. I got this. I got this. I got this. Just relax. I got this. I'm gonna do this before I go to bed. It's gonna happen. It's gonna happen for sure. It's just, I gotta abuse references here. Okay, let's do this. 153 and 88. How does this even make any sense? Where's 9, mate? Okay, where's it? 88. This, right? Of num. Okay, so now we have 135 and 89. Great. Now, what is the limit bound on this? Two and six should not talk to one another. Yeah, this is not how this should be. And also I should be updating lower and upper every time. Yeah, because 2 plus something, I might, yeah. Here, well, I less than n. It's not the case that lower less than or equal to break, otherwise min of lower, comma num minus sorted num, sorted index equals sorted nums at index I. Upper equals max of upper num plus limit. I don't know if I can really. Maybe I make it a min, whereas I make it tighter to do. Swap min slash max functions. Anyways. Actually, no. The point is that like you're able to chain. I think that's good. Probably not. Good. Here we'll do sorted num, df sorted index, component, I plus circle 1. Alright, 135 and 89. 112, 6, 7, and 18, and every single index points to its corresponding component. Is this good though? Oh no, oh yes, this is good. 0 points to that. 1 points to 6, 7. 2 points to 6, 7. Beautiful. Oh, this is beautiful. This is beautiful. Oh, this is gorgeous. This is what we like to see. Okay. Now we can do return. Here we'll make this guy. If anything. Component. Sorted order. Since we want minimum each time. Reverse. I don't know if I can do things this way. Maybe I might be able to get away with it. Is there a dot reverse function? Ooh, there is. Oh, that's cool. I didn't know that there was a reverse function. Now we can just do return the pop and range n. Oh, hallelujah, hallelujah, hallelujah. Print is going to become hashtag print, run, and submit. And there we go. Completion streak 193 days. Consistency is key. See you tomorrow. Okay, feels good. Yeah, okay. Damn. So like at some point like I've kind of had like all the ideas of the solution at like separate parts of solving the problem, but never together, right? I didn't connect the I don't know. I did think of it like a graph where it's like, you know, you end up like searching the dependence. The core thing I didn't think about was connected components. Yeah, that is the key thing that I was missing. I pretty much thought of everything under the sun, where it's like, you know, I thought of turning this into a graph problem. I thought of the idea where it's like, okay, you always want to grab like, you know, instead of a chain where it's like if you have a list of dependencies, it's like you kind of grab the smallest one in there because it's like that will be like essentially for each index you want to make it like, you know, the smallest possible number you can possibly make it, because that will have the biggest effect in terms of making this lexicographically smallest, right? But yeah, it's just I kind of thought of everything in here except for the fact to make this to turn this problem, to think of this as a graph problem, and additionally on top of thinking of this as a graph problem, thinking about connected components. That became a little bit of a stretch for me, and I didn't think about that. But nevertheless, as always in my videos, I do a quick recap of how I was able to solve the problems. For this one, I ended up needing to look at the hints. As I was just explaining, I did think of most of the ideas that came from the hints. I thought about turning this into a graph problem. I thought of essentially recognizing that at every single index, I will want to essentially swap it with whatever is the smallest possible value I can put in there, which may require more than one swap, right? So like, you know, for example, here inside of nums here, we see that 52 is the second index, right? But 52 minus 14 is what? 48 minus 10 is 38, right? And obviously here we have a 27. So 27 and 52 are not directly interchangeable, but that's because you need to swap 52 with 38, in which case you can then swap the 38 with the 27, right? So there's essentially like a list of dependencies that you need to follow, which is how I initially came about trying to think of this as a graph problem, but I didn't end up actually like, you know, like I thought I was going down into like, you know, a weird idea where I was like, okay, maybe since yesterday's problem was a graph problem, maybe this is another graph problem, but it started feeling like a little bit of a stretch. Turns out that was kind of the right idea thinking. I just didn't realize it. And yeah, the little bit that I missed is thinking about this problem in terms of connecting components. But nevertheless, let's kind of explain what I was able to do. So, okay, here I can kind of get rid of this function. We can clean up the code as we explain it. Yeah. This is useless. Okay. Num. Yep. So here we're good. Yep. You can do this. Probably can do this. Okay, probably can do this. Only smallest values. Yeah, in other ways I could use the collections.deck and so on, but yeah. Let's clean up the code so that we can explain things a bit better. There we go. Yep. This is all great. Minus limit less than lower. Or sorted num minus limit. If sorted num upper sorted num plus limit. Yep, this is a probably not. Yep, this is no longer needed. Yeah, we can probably leave it as is. There we go, bada bing, bada boom. Okay, sweet. And now we're at 63.20%. Okay, so we're right in the standard deviation curve, so that feels nice. Okay, so we can explain, we can continue explaining the solution, sorry. So essentially, yeah, the idea, kind of as provided in the hints, is that essentially you need to think of things in terms of connected components. So the reason why, again, I thought of this in terms of a graph problem is because essentially you're allowed to swap two nodes, essentially if and only if, or two numbers inside of the array, if and only if their difference in value is less than or equal to limit, right? And now, what this means is essentially you can connect every single two numbers, kind of like in a graph, where an edge between the two nodes essentially would represent that you can swap those two nodes, right? And then now that might not be every node, right? So obviously if this was in terms of indices, right, as long as limit is 1, then essentially you could bubble sort the entire array and you're able to always reach a sorted array. That's awesome, right? Here you can only swap numbers if their absolute value in difference is less than or equal to limit, which is a big change and a big deal, right? Because you might not always be able to swap with everything, let alone things that are adjacently directly next to you, right? And so what you kind of want is visualize, a mental model like a graph inside of your mind, where essentially you have every single number in its own node, and essentially an edge between two nodes represents the fact that you can swap those nodes, right? And so then if you can think of it as a graph in that way, where essentially like any undirected edge between two nodes means that they can be swapped inside the original array nums, and you want to make this lexicographically as small as possible, which means you want the smallest possible numbers at the beginning and largest possible numbers towards the end, and especially like like something like 1 9 8 7 6 5 4 3 2 1 0 like this is much better than something like 2 and then 1 3 4 5 6 7 8 9. Even though like more of this array happens to be sorted, this one is better just because there's a 1 at the front, right? So the idea is that essentially the very first value inside the nums array, you'll want to make it as small as possible, right? And then once you made it as small as possible, the next element in the nums, you want to make it again as small as possible. So you want to be very, very greedy in that idea, because again, it's about lexicographically smallest, right? And whenever you compare two arrays, it's lexicographically smallest based on the first value where the things differ. So that's why it's important to make the initial values as small as possible as you can, right? Again, something like this is lexicographically smaller than something like this, even though a huge part of this array is sorted, right? Like here, every single number is smaller than every single number here, except maybe the last one. But again, doesn't matter whether this starts with a 1, this starts with a 2. This one is the lexicographically smaller one, right? So you want to be greedy in terms of putting the smallest number you can at the very front, smallest number you can at the second very front, etc., 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 right? So if you think of this graph, where again, nodes are the numbers and edges between them represent the fact that you can swap them, then essentially you want to go through the number in nums, right? And then figure out which connected component this number belongs to, right? Because essentially a connected component will be like a set of nodes that are all connected, right? And then out of the connected component that like a number might belong to, you want to go, okay, I'd like the smallest one, right? Because inside of that connected component, essentially represents all the nodes that could really take place at this single position, right? And we know that no matter what, we want to put the smallest possible number that we can at the very front of the array, right? So we grab the connected component for, the very first element, and we say, hey, for that connected component, I'd like the smallest value, please, right? Because I want to be as greedy as I can. I want to make this as lexicographically small as I possibly can. So out of all the options that I can swap this number with, I want to swap it with the smallest one. So again, if we think of this mentally in terms of a graph where there's an edge between two nodes if and only if those two nodes can be swapped, which again is only the case if their absolute value difference is less than or equal to the limit, then out of that node, we find its connected component, which essentially represents, a set of all the nodes where every node in that connected component can swap with one another. So it's like, okay, this node out of all the nodes they can swap with, okay, let's make sure that we swap it with the smallest one, so that way we can reach towards our goal of making this as lexicographically small as possible, right? And so that's exactly what we do. Where here it's I'm going to loop through every single node inside of num. So while I is less than n, starting with the very first one, what I'm going to do is I'm going to have the nums sorted, because as given by hint number 4, if I have nums sorted, then I essentially realize that okay, I'm going to essentially get the connected components in batches. Simply because the connected components are essentially the edges are defined by this constraint over here. So by sorting nums, I can actually abuse that mechanic a little bit, and that way building the edges or building the connected components only takes linear time instead of quadratic time. Again, I think this is generally a pretty tough medium. I wasn't able to solve it on my own without hints. And this is a lot of things to think about. It's not impossible, and it was definitely close. I definitely, maybe I could have gone towards that idea of connected components at some point, because I did get close in terms of thinking about graphs and so on. But it is a pretty big leap, where it's you have to realize a lot of things, and they're not impossible to realize, especially not individually. But tricky, definitely tricky, and I wasn't able to do it on my own tonight. So definitely a tricky medium. But yeah, once you essentially, once you have the nums sorted, then essentially you'll have everything in batches, right? Because it's if I sort these nums, I'll essentially have 1, and then the next smallest number will be 3, and then it's I can ask myself, okay, from 1 can I reach 3? Okay, I can, good, right? Because limit is 2. And then after that, it'll be 5, and it's okay, from 3 can I reach 5? And so then that's good, right? If anything, I don't even need this, right? Or lower upper. Here, yeah, this makes my logic simple, but here I might not even need to do this much if statement logic, because of the fact that the numbers are increasing, right? Yeah. Yeah. Belongs. Components, right? There we go. And now we can ignore this. Yeah, I just realized that as I was explaining that right now. Yeah. Update upper bound. Actually, this will always be guaranteed. Upper bound equals sorted num plus limit. Yeah, that's always guaranteed. So yeah, I can remove those couple if statements, checks, and so on. Okay, and that actually makes my code even faster, 83.833%, which is very nice and handy dandy. So yeah, The point is that, again, since I have the numbers in sorted order, then essentially I can essentially keep checking, like, okay, does it keep belonging in the same connected component that I currently have, right? So here I'm going to start off with, like, I is equal to 0, and then every single time while I is less than n, I'm going to say, okay, let's create a new connected component. So let's grab that, like, the number and the index of that number actually maps to in the original list of nums, because you'll need those inside of sorted nums, right? You sort the nums, but you remember their indices that they used to be inside of nums, because that'll be very important later on. And then here you always define, an upper bound, which will be num plus limit, right? Because it's like anything that essentially overlaps with that, like, is that or lower and so on, then it's being chilling, right? Essentially, it'll belong in the same connected component because those two are swappable, right? And again, since we have sorted nums, the nums are sorted increasing, we only have to think about the upper bound. We don't have to think of a lower bound as I was doing before, right? So that's essentially why I was able to remove that logic. Otherwise, we have I plus or equal to 1, grab the current number and put it inside of our connected component. Here we'll say, okay, we'll introduce a new index here inside of our dictionary here that will map, like, index to component, connected component mappings, which is why we need those indices from sorted nums. And so here we'll say, okay, we just created a new connected component. Obviously, this index will map to this connected component because it's the very first number inside that connected component. Because again, we're going to map the original indices instead of nums to their connected components that we built. That way we can loop through all the indices of nums from the original numbers and essentially be like, okay, from its connected component, grab the smallest one, etc., 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 right? So here we'll just be like, okay, while we still have items, we're gonna say, okay, let's grab, like, the next sorted num. If it's not in the same connected component, so if sorted num is greater than upper bound, then just break, right? Because if it's greater than upper bound, then it means that it's like, okay, it's no longer connected, right? The discrepancy is too high. Upper bound represents, like, the current largest number in the connected component plus its limit. And so if the sorted num already right off the bat, can I do... No, yeah. Now I'm being dumb. Oh, because it already has limit inside of it. Yeah. So yeah, if sorted num is greater than the upper bound, which is like the previous number plus the limit and so on, then obviously it belongs to its own new connected component, right? And so here we just break out of the while loop. And then here is just like, okay, every single time we're going to update the upper bound, right? It'll be sorted num plus limit. Why do I now have to check if it's an if statement? Because again, the numbers are sorted. So, like, sorted num is now the new biggest number that we essentially have inside of our connected component. So we're going to take that plus the limit is essentially the new upper bound, right? And then if we ever come across a number that is, like, too large, then it's like, okay, it'll belong inside of its own connected component. And by the way, the reason, again, I don't do sorted num minus limit is because, like, the point is that, like, two numbers need to be limited apart. If I did sorted num minus limit is greater than upper bound, which already includes limit, then essentially I would allow for numbers that are, like, less than or equal to 2 times limit in terms of their absolute value. I only want to allow, things that are less than or equal to limit in terms of their absolute value, right? Here's, like, if I had the numbers 2 and 6, right, and my limit is equal to 2, then it's like, my upper bound will be 2 plus 2 is equal to 4, right? Now, here if I did, like, 6 minus 2 is equal to 4. This is great, this is fine, but no, 2 and 6 are 4 apart. They're not definitely 2 apart, so I definitely can't allow that, right? So that's why essentially I check that sorted num itself must be greater than upper bound, not minus limit. So just trying to make that clear. Otherwise, we'll update upper bound, and again, no need for an if statement because sorted num is the greatest number that we've seen so far. And every single time it's like, okay, let's add the sorted number into our connected component. Let's map the original index of that sorted number from the original index being the original index to that number from the original nums variation, not the sorted nums. I map it to the very same connected component, and then just do increment the index for the while loop, and there we go, bada bing, bada boom, right? And then once we're very done building that connected component, here we reverse it, just because again, we'll want to always grab the smallest element later on. Since, again, we're visiting the numbers in sorted order, these connected components will be sorted in increasing order, so we reverse them, so that way we can call dot pop every single time that we want the smallest element later on, right? Another way is essentially I could have made this like, a collections dot deck here, or I commented this out, and here I could do pop left, right? And something like this will work just fine, right? But yeah, so I'm thinking that collections.deck usually ends up being a little bit slower, so that's why I kind of decided to choose to avoid it if I could, because a lot of the times just using the default Python stuff ends up being just a tiny little bit faster. So there we go. So now we're at 75.7%. There we go. Bada bing, bada boom. A little bit of deviation there, but nothing to worry about too much, right? Otherwise, what we're going to do at the very end is essentially it's like, okay, we have the mappings of every single index in the original list of nums to its connected component, right? And so instead of a connected component, essentially, represents like, okay, for every single index in nums, we're able to map it to its connected component, which is essentially like, a list of values, which happens to be in reverse ordered order now, that essentially it can swap with, including itself, right? So what I will do is grab the minimum in that connected component, because again, we're going to build this result, from left to right here. And so it's like, obviously we want the smallest possible values we can have at the very beginning. So it's like every single index, we're going to be like, okay, let's look at all the values that I can essentially swap myself with, including my own value, and grab the smallest one, right? Because we want to minimize our array in terms of lexicographicalness, right? Make lexicographically smallest array by swapping elements. So it's like we're always going to keep grabbing whatever is the smallest available number for the smallest indices that we can every single time. So it's like, okay, look up the connected component that a number belongs to using its index, which is why we essentially kept the number and index mappings from the original numbers instead of assorted nums. And it's like, okay, for each, we're going to look at its connected component and grab the smallest one. Since I reversed the connected components, which used to be in sorted increasing order, now they're in decreasing order. So that way I can do dot pop to essentially get the minimum one every single time. So it's like, d of I for I in range n. So like for each index in nums, we'll look at that index connected components of values, which includes itself. Grab the smallest one by calling dot pop, because we have them reversed when they were in sorted order initially, and we'll do that for every single index inside of nums. So that way, for each single number in nums, we'll have the new value be whatever is the smallest value currently inside the connected component for each index, right? And as you can imagine, it's like, as you go through the indices, you kept popping stuff from the connected component, so less options are viable as you go on. But that's fine, because again, you always want to grab the smallest possible number you can at every single index along the way, because the smaller the index, the more important it is to have a smaller number to make the array as lexicographically small as possible. So there you go, bada bing, bada boom. That is pretty much it in terms of how I was able to solve this problem. So hopefully my solution is at least somewhat clear. I know I might have not done the best job to explain right now. Although, yeah, it's because my eyes are burning a little bit, and I'm ready to go to bed, let's just say. But, at least I hope that my solution made some sense in any way, shape, or form, because that would be absolutely awesome. And if it didn't, let me know down in the comments below, and I'll make sure that when I come back tomorrow, I'll be able to maybe clarify a few of the details here and there. But otherwise, that's pretty much it for this video. If you did find it useful and enjoyable in any way, shape, or form, I would highly appreciate it if you left a like or a comment. But otherwise, I'll catch you in the next one. So until then, ciao ciao, my friend. Bye bye.